Let's shift gears now and leave the world of electrostatics. And let's start putting charges in motion. Now is where we do currents. But we're going to make a move in a specific way. So let me introduce a new quantity. We'll start a new unit called current and current density. Current and current density. So our charges are going to start to move, and we're going to introduce the concept of a current, something with units of amps. And units of amps, I, are really just change in charge with respect to time. Coulombs per second. That's what an amp is. And this is the quantity that we'll be dealing with. Now, when you studied physics, remember, just as we had point charges and volume charges and surface charges and line charges, so we also have a lot of different ways of describing current. We have line current, and that's usually what the term I is used to denote. You know, if you have like a circuit diagram, for example, where you've got a single trace and an I going through that trace, you're assuming that the current essentially collapsed to that line or pathway, and you're not worried about the geometry, the cross-sectional geometry of what's going on. You can also have a current density and some of you may recall that that is J vector and has units of amps per meter squared. So it can be a function of three-dimensional space. So let's go ahead and put an R vector dependence on there. And it is itself a vector that points in the direction of which way charges are traveling. So the magnitude tells you how many amps per meter squared, and the direction of the vector tells you what direction they're traveling. You can convert between these two. If you ever want to collapse this down to the kind of I that you would find in a circuit, you can always get total current by taking what looks to be a surface integral, very similar to the kind of integrals we looked at in Gauss's law. We take a surface, and it does not have to be, in this case, an enclosed surface. It just has to be some sort of diaphragm. It can have undulations galore in it, or it could be completely flat. But the way that you calculate it, you take your J vector, you dot it into the surface normal, just like a flux integral, and basically you count up all of the current density traveling perpendicular to that surface. And of course, the idea being is that if you've got a vector here and your surface is like this, you only want the normal part. The tangential part is just the current that's kind of sloshing around the surface. It's not really going through the surface. So if you just count the normal part across all of these surfaces, all these points of the surface where you've got current going through, you will get a total value in amps. That makes sense, right? This is amps per meter squared. You're integrating it around a surface, something with meters squared, basically, units, and you should be left with amps at the end. Now, there's also an intermediate form here. This is a volume current density. Every once in a great while, you'll even see a problem worked where you have a current sheet density, or a surface current density, as it's often called. And that, for some reason, we always give it the value K vector. And that has amps per meter. And sort of You can think of it as this is to a point charge, as this is to a line charge, as this is to a surface charge. So those are the fundamental units of charge. And the key part that we want to emphasize here is that if you do decide to enclose this integral, for example, let's say I have a volume V and an enclosing surface S. So now I write a surface integral that encloses that volume with the surface S. If I perform that same computation, the total current through there, I get one of either two scenarios. I should get 0 if there is no charge storage. And I will get some change in charge if that does not go to 0. So I basically have the 0 case and the non-zero case. And that makes sense, right? From a geometrical point of view, if I've got current densities swirling around in space, a vector field that describes how my current densities are flowing, and I count the amount of current that's going through this volume in space. Well, anytime the vector points in to the flux integral, I'm going to get negative contributions to this integral. Anytime it points out, I'm going to get positive. At the end of the day, if all the positives balance out with the negatives in this flux integral, I should get no net change in charge. And that's the case of no charge storage. If, on the other hand, that doesn't balance out, that can happen in life. That happens all the time. But what that means is that charge is building up somewhere within this volume. We can't tell where, but by conservation of charge just doesn't disappear in this world and then come back. It's got to be balanced. It's never destroyed. And so, by process of illumination, if this integral is not 0, something is building up. We might not be able to tell where or how much. Well, we can tell how much. We just can't tell where in the volume. So what we're going to look at for the next couple of weeks is the magnetostatic case, in which we have charges in motion, but this is true for any volume that you pick. The charges are moving, but there is no charge being built up in anywhere in space. And of course, there's a nice partial derivative expression for this. We've already applied the divergence theorem to Gauss's law, right? What can we... Let's see, how do we want to do this? Well, remember, the divergence theorem says that if I have a closed flux integral of this variety, and remember the divergence theorem is purely mathematical. It has nothing to do with the actual physical quantities here. We can just apply it as if it was an algebraic relationship. We learned in this class that this is actually the same thing as integrating across the volume of the divergence of that vector. Do you remember that? It's a simple mathematical relationship that you can commute the result. And if this is 0 for all regions, for any possible volume you can think of, then the magnetostatic condition could be written even more elegantly as the divergence of J is always 0. That's case number 1. If it's case number 2, then this is actually the change in volume charge density instead. But we're not going to get to that point. So don't forget, don't bother with that. That last thing, when that's put on there, that's called the continuity theorem. It basically says that no charges cannot be created or destroyed. It's a very elegant way to write it. But then in the end, that's all it says. This is the kind of scenario that we're going to look at. We want to do this because we've been talking about electric fields, but we know from physics that there are also these magnetic fields. Whenever charges are in motion, you get a magnetic field. How does a magnetic field? Do you remember your right-hand rule? So this is the one where the finger curling right-hand rule is useful, right? When you're doing right-hand rule for cross products, you take the first vector, the second vector, and you get the third vector. This is the one I always use. Here's an example where this type of right-hand rule is a little bit more useful. Basically, if I have a current in space, thumb points in the direction of the current, and the magnetic field swirls around that. If I have a charge that moves through that magnetic field, it will experience a force perpendicular to the field. So if the field comes out like this, and the charge is moving this way, it will bend towards the wire that created that. Now, one quick point that I'd like to end off with. Yeah, sure. Let me draw it on the board. It's useful to have. In fact, let's do a little thought experiment while we're up here. Because I want to make a point that I think sometimes is lost in all the hairy details of electromagnetism. If you've got a wire with currents in it, say the current is going this way, magnetic field should come out of the board up top and go into the board at the bottom by the right-hand rule. Out of the board at the top, into the board at the bottom. The tip of the arrow coming out, the feathers going into the board. That's kind of how I remember that. If I have a positive charge, and let's say with this particular geometry, it starts moving. Well, let's see. B field, or magnetic field, points out of the board. The charge is pointing this way. So it's velocity times charge crossed into the B field will give you the force vector on it. So this thing will actually move down towards the wire. The faster it moves, the more force that gets exerted on it and draws it closer to the wire. If I flip this, if I turn this into an electron, it will actually do the opposite. It will bend away. It will bend away faster as I travel it faster. I have a quick little thought experiment to do for you. This current in the wire is really just electrons moving, right? In fact, the electrons are actually moving the opposite direction. Because Ben Franklin got it wrong. He had a 50-50 shot and he blew it. Yeah. So it's the electrons that are carrying the charge, and they're negative. And the protons are just kind of in a solid state material, holding steady, these positive charges, and they're watching negative charges zip by. In this case, they're zipping by this way. So you have all these negative charges. And let's assume that for the most part, this thing is in charge balance. Same number of negative charges as I have positive charges on my nuclei of my atoms making up this material. And it's the net motion that causes the current I to be observed. Now let's slip into a different velocity frame, a different frame of reference. Let's start moving with the current. So in step 1, I'm going to have a positive charge that's moving at velocity v. And it's going to bend down toward because of the magnetic field due to the current. In step 2, or situation 2, I have the exact same scenario, but now I'm going to accelerate my frame of reference so that now I'm going to be moving at I accelerate into the constant velocity frame of reference aligned with this positive charge up there. So now I have a positive charge that's not moving. How much current is flowing through that wire now? It's actually the same amount, right? Because let's say I start moving faster this way. The electrons look like they're zipping faster by, but now the protons are moving that same velocity as well. So the net charge in coulombs per second is going to be the same regardless of which reference frame I'm in. It's going to be the same I. But that's peculiar, right? Because in this scenario, I said, oh, look, the velocity of the positive charge moves this way. It's going to bend towards the wire. If I go over here, in this frame of reference, it looks like this thing is standing still, and the current is the same. So what does the thing do? Well, unless we live in two parallel universes, it's better start moving towards the wire. But how can you, if there's a same magnetic field, same current, same magnetic field, why does this thing move towards the wire?
It's just like if your two cars are driving at the same speed, they're still moving. It's just the frame of reference.
True, but if I just gave you the problem in this frame of reference, I say here's a current, same amount of charge per second, moving through space, net charge per second. It's got the same magnetic field around it. I now have a charge here, but it's not moving. It should be dropping. You're right, it should be dropping, but what force is acting on it?
Is it magnitude because of the current is electrons?
No.
It's by Newton's third law, right? Because now my velocity is not from the charge, but from the wire. So I still have V pointing out that way. I still have V pointing out.
Yeah.
I still get the force going down.
So here, the explanation is actually, you're right in the sense that we would expect these two systems to behave exactly the same, and they do. But here's the kicker part. We actually have to use relativity to explain it. What's actually happening is that as I move in this direction, I'm Lorentz contracting. You remember that term from physics? I'm Lorentz contracting the wire, and because the protons and the electrons are at two different velocities of propagation, or velocities, the electrons contract a little bit more because they're going faster. And now it looks like there is a negative charge imbalance because the electrons are compressed more than the protons, which are a different frame of reference. So what it looks like is that this is a negatively charged wire, whereas it looks charge neutral in this frame of reference. And there is an electrostatic force that actually pushes that through. It's the exact same force, the exact same motion. But by slipping into different relativistic frames of reference, you can actually change a magnetic force into an electric force. And this is really why when the physicists talked about the four fundamental forces, strong force, weak force, gravity, and electromagnetism, they lumped the electromagnetism together. Magnetism is really just electric charges acting with with the effects of relativity. Just something to think about while you're mulling over your electromagnetics class until Thursday. So let's recap where we are today. What we did last time, we finished up, I think I did a really long example on how to apply Laplace's equation to a capacitor problem. And then we said, oh, look, we can use this to calculate things like capacitance between two strips of metal, which allows us to do capacitive touch screens and the like iPods and that, or iPhones and that sort of thing. That was kind of an instructive example. And then the last part of the class, we introduced the concept of currents and talked a little bit about magnetic fields. So what I'm going to do today, we're going to finish up our talk about current and current density, our introduction to when charges move. And then we're going to get into the Biot-Savart formula, which is how you can calculate magnetic fields from a current distribution. It would look extraordinarily similar to lecture that we gave on Coulomb's formula, because you make just a slight change and you put currents instead of charge into the integral. But voila, it looks almost exactly the same when you get down to it. So all that stuff that you've been learning to do, first with your Coulomb integrals, then with your voltage integrals, by the time we do Biot-Savart law, you are going to be an expert. And you can calculate any field quantity from just about anything. Charges, currents, what's the total electromagnetic field in that scenario. So yeah, you guys are starting to get kind of dangerous in your abilities. So any questions before we get into the lecture? Did you have a question, Mike? What did you say? Oh, I did. You can just, before you walk out, just throw it up there at the front of the room. Just throw it on the folder or in the folder. Any other questions before we get started? Okay. Well, we were a little bit rushed at the end of last class period, but you'll recall that I was making kind of an interesting physics point that maybe you have seen in your physics class before, but it's to drive home something in our discussion of magnetostatics. And that is, at the end of the day, in electromagnetism, there is just one force that we study: the repulsion and or attraction of charges. Like charges repulse, unlike charges attract. And even though we're introducing this concept of the magnetic field, we talked a little bit yesterday about how a charge that's moving, it bends towards this because we have a magnetic field circulating around this wire via the right-hand rule. Let's see. B field comes out, charge goes this way, so this is going to bend down. They said when we accelerated and slipped into the same frame of reference of that particle that was moving so that it looked still, and of course had that exact same current, there was no velocity in that particle, and so we would not expect any magnetic forces to act on it. However, these are just the exact same problems viewed in the same frame of reference. This still should accelerate towards the wire. And what we said was, when we slipped into this frame of reference, the Lorentz contraction of the electrons traveling in here, because we were accelerating, they're now traveling at a higher velocity with respect to our frame of motion, causes them to contract, and this actually gets electrostatically negative, which winds up attracting this with the exact same force as what you would have seen here that caused the particle to bend inward. And that was sort of like one of many little thought experiments you can do to introduce the fact that a magnetic field is really just an electric field if you just change the relativistic frame of reference. They're really the same force. Add in relativity, and all of a sudden electric Coulombic attraction and repulsion turns into magnetic fields and magnetic forces. And of course, all this time we're discussing force, which is equal to a charge, scalar charge, times its velocity vector, crossed into the magnetic flux density. We call this the magnetic flux density in electrical engineering. And the H field is a quantity related via this permeability in Henrys per meter. B field is Webers per meter squared. H is amps per meters, and we electrical engineers call this the magnetic field. And we electrical engineers like this kind of terminology because it creates a really nice symmetry in the vector quantities that we analyze electromagnetism with. You got E and H, that's your electric field and your magnetic field. You got B and D, you got your magnetic flux density vector, and you got your electric flux density vector. And there's a beautiful symmetry to solve problems. And that way of parsing Maxwell's equations and kind of setting them up is particularly good for dealing with engineering problems, particularly those that involve the interfaces between junctions, like dielectric 1 and dielectric 2, because it's very useful for establishing and analyzing boundary conditions. Now, if you are a physicist, you hate this, because a physicist says, you know, the forces on a charge, the total forces on a charge, are really going to be just equal to q times velocity crossed into b plus that charge itself times the electrostatic field. That's going to be the total force. So force is something we can observe. We can put a charge and see, you know, what's actually pushing it and measure it directly. And these other things like b or h or d are derived quantities. They're kind of constructs that we use to analyze fields and materials. And so for that reason, physicists only use these when they study electromagnetics problems. And because the electromagnetic field, B fields are really just kind of E fields in disguise when you make a relativistic frame of reference change, hardcore physicists only use E. So whenever you read a paper or a magazine article or something, you always tell who wrote it by what they're actually doing. Is it a hardcore physicist? All of the electromagnetism is described in terms of E. Or sometimes even that, they skew that and they'll use electrostatic potential, V, basically. They might change the variable name, but they'll just use your voltage function. And then another vector function called A, which is the electrodynamic momentum of the system. But anyway, that's the hardcore physicist. This is just the normal physicist. And then everything is the electrical engineer. Because at the end of the day, we don't care about, like, if something is a useful construct and it helps us solve our problems, why do we care? You've taken in courses where most of the computation was done with imaginary numbers. Can you measure a J in reality? No, but it's just so useful, so we have no shame in using it. We don't really go off the philosophical deep end and think, oh, is there really such a thing as a J? So anyway, that's my little backdrop for kind of referencing and orienting you so that you know the difference between like an engineering text and a math text and a physics text, or papers coming from those different communities. Okay, so good. Now, before we finish off our discussion of current and current density, I am going to derive one formula here that's just so fundamental to electrical engineering. We now know kind of where it comes from based on all the stuff that we've studied so far. So I can't help but just go through how we arrive at it, because it's just so fundamental to engineering. And that is, of course, Ohm's law. So let's do a quick discussion of Ohm's law based on our constructs, just to show you how much we've actually accumulated in our electrostatic and magnetostatic tool set. So I'm going to start with an irregular prism. And by irregular prism, I mean that I'm going to take some weird area shape like this. It'll have area A in units of meters squared. And I am going to extrude it at a right angle to make a prism. So that same area is over here. These are perpendicular to the area. The edges that I've drawn should really be a right prism in my description. And this length with it here we will call L. And what we're also going to do is metallize the junctions here. And of course, that's nice because whenever you metallize something, you pretty much assure that the entire surface is at the same potential. Why is that? Well, because good conductors don't allow E fields inside of them, right? As soon as you impress an E field, the charges stretch out and instantly counteract the E field so that the E field is always 0. What that means is that I could start here on this piece of metal, and no matter where I go, I'm never going to accumulate any E field if I stay on the metal, and therefore the potential is always the same at this part of the metal, and that part of the metal, and that part of the metal, that part of the metal. So I can call this one potential, call it V sub 2, for example. And over here, I can call this V sub 1. Okay. Now, what else do I know about this? Well, presumably I don't have metal here. I just have an arbitrary substance. It could be a dielectric, it could be a good metal, it could be a cruddy kind of metal, a semiconductor. We know from physics that J, our current density vector, is equal to the electric field. Remember, this has volts per meter. This has amps per meter squared. And of course, what kind of units does that constant have to have in order to get this to hold? Let's see, I need a meters in the denominator, so it's going to be something per meters. And then I got to take voltage and turn it into an amps. So it's got to have 1 over R, 1 over ohms. So I can write that as an upside down omega. Mhos. Siemens per meter is the actual definition. And this is the conductivity. We've found that most materials can be characterized with a simple constant of proportionality to describe how much current density flows through them as you impress a field upon them. And of course, you have to keep in mind that that current flow is a statistical average, right? The electrons themselves, when they're impressed in an E field, what do? They accelerate. They don't move at a constant velocity. But of course, what happens when that happens in material? They accelerate, and shortly thereafter, they crash into something. And they're shaken up, they bounce off, they shake it off, and they start accelerating again, and they crash into something. So statistically, depending on how much stuff is in the way and how many free electrons there are to crash into stuff, you'll get a value for sigma that represents the average net flow of current density, amps per meter squared. And so that, all of that crashing and statistical behavior is sort of wrapped up into this one constant, which tends to be a constant for constant temperature and the same type of material in here. So that one you probably recognize that equation from physics. So let's go ahead and do something here. We know that J is equal to sigma times E. And I'm going to make a little flux integral on both sides. I'm going to integrate let's see, I'm going to do this across area A. And let's see, whatever I do to the left-hand side of the equation, I had better do to the right-hand side. So I'm also going to integrate this across the same cross-sectional area A. So I'm going to just pick a surface here in my prism of A, somewhere along there. I'm just going to integrate it, my current density and my electric field times my constant sigma. Well, this we recognize, this was our definition for total current. We have amps per meter squared. We're integrating through this. So if we're in a typical magnetostatic situation and no charge is building up, then whatever current I'm feeding by wire to that metallized surface, total current I, is what's spread out and conducting along that prism. That was our definition of current, yes, that we introduced 2 days ago. Over here, this I have to be a little bit more careful at. What have I got here? Well, let's see. If I look at this from the side, so here's area up at the top, and that is at V2 volts. And here's an area at the bottom that was also across the same cross-sectional area, unit L away. And down here I have V1 volts. Then I know that the E field here is going to point down this prism. And I'm going to invoke a little approximation that we invoked earlier, and that's for the parallel plate capacitor. Whenever I have a voltage here and a voltage here, I could do this by invoking the parallel plate capacitor. I can actually try to solve Laplace's equation in one dimension. But I basically can show that the E field here is constant and it always points down. Now, if you remember that result, E field here in this case is V2 minus V1, or the voltage drop across the device, divided by the total distance L. And I say that's an approximation. Of course, that would also be in the downward direction, so they put a little negative Z hat there. Now, there would also be fringing fields there. The farther apart these plates become, the more kind of an approximation this expression actually becomes, because you get some fringing fields out here that, and some irregular behavior at the edge. But for the most part, this is a good approximation. E field is down. It's related to this geometry and the voltage drop between the two plates. And for the most part, it's constant, no matter where I'm at in between these two plates. We've seen that before in our parallel plate analysis. Yeah?
Why is it down?
Let's see. So I am assuming at this point, the way I've defined the voltage drop, V2 minus V1, that V2 is a bigger voltage and V1 is a smaller voltage. That's right. Well, yeah, I'm going to define my voltage drop, so to speak, to be there. If this turns out to be a negative number, then you're right, the whole problem just flips up, and I've got to draw the other way. But for the sake of illustration, I've kind of resolved the direction, so to speak, based on this convention. So, okay, E field is pointing down. I've got a voltage drop from here to here. I just divide that voltage drop by the L, and that's what the quantity is. Now, because it's a constant, I can actually rewrite this integral. Well, this is a constant, we said, so I can take that constant out. I've got V over L here, and it's pointing down. Well, you know what? If I'm taking a flux integral across this surface, and my surface normal is pointing that way, that aligns conveniently. And really what I wind up doing is, we could say, taking an area integral with nothing inside. Well, that should evaluate to the area, actually, if everything's lined up. We're just sliding around, picking up all those constant contributions of E field. And so, rewriting this result, I get I is equal to voltage times this constant of proportionality that only depends on geometry and material. If I rewrite this again, I get L over sigma A. And of course, that's Ohm's law. We all recognize that instantly. V equals I, and I guess this must be R. The fundamental law of electrical engineering. Well, one of them, right? There was actually a question on the Army Corps of Engineering exam many years ago, and it said, what are the 3 fundamental laws of electrical engineering? And a lot of the people kind of scratch their head and look at it. If you look at the answer key says V equals I over R is the first one. V over I equals R is the second one. And I think I equals V over R was the third one. Those are the three fundamental laws of electrical engineering. I am not making this up. I am not making this up. You will not get a question nearly that easy on your next exam, so don't study the Army Corps of Engineering Solution Manual for this next exam. Yes, Cameron.
When you were calculating the E field between the two plates,
That's right.
Did you have it in the negative Z hat direction?
That's right. I kind of put it in the negative Z hat because if I'm defining this to be the voltage drop from here to here, then assuming that's positive, the gradient, remember E field is always negative the gradient of your voltage drop, so that means it'll always point down. It always points downhill, so to speak. If, however, I put this as a minus up here, then that'll flip the sign and make it point up. Now, that's interesting. Not only do we get Ohm's law, but we actually get a bonus when we do this. We get an expression for calculating resistance, actually relating it to the fundamental quantities of conductivity, the length of the channel, and the cross-sectional area. And it makes a lot of intuitive sense, right? You know, why is sigma on the bottom? Well, as conductivity increases, as there's more free charges or less collisions as those charges move through the device, then sigma increases and you'd expect resistance to decrease. That makes sense. And of course, these geometrical factors are very much, they lend themselves to that old-fashioned electricity traveling in a wire is kind of like water in a pipe analogy, right? Oh, if I have longer to travel, of course I'm going to have more resistance as I send that current across a channel. Double the distance, double the resistance. That makes sense. And the cross-sectional area is there, but it's in the denominator. That makes sense too, right? I can carry more water, so to speak, if I have a bigger cross-sectional area. The total resistance will go down. And let's see, does the do the units work out on that? We had 1 over ohms per meter, so that becomes ohm meters in the numerator. And this is in meters, so that's ohm meters squared. And this is meters squared. Yep, we get ohms. Everything is right with the universe, right? So any questions? Any questions before we go on? Well, good.